So far in this chapter, we have basically discussed the uniform topology or topology of uniform convergency when we have considered some power x to the power y. Basically, uniform convergency topology measures the distance between two functions. In this module, we shall discuss two more topologies. One is topology of compact convergency and another is compact open topology. We shall also discuss another topology which is called topology of pointwise convergency. In fact, topology of pointwise convergency is nothing except product topology. It is in some different form. So, let us go to slide presentation. As we have discussed, let us start with the following definition. Let X and Y be two topological spaces and X belongs to capital X and U be an open set in capital Y. Let us denote the set SXU is equal to all those functions f from x to y such that fx belongs to u. It can be easily verified that the sets SXU form a subbasis for some topology on y to the power x, which is called topology of pointwise convergency. If we note minutely that here the topology of x has not been used to introduce the definition, only the topology of y has been required here. Now, taking all possible finite intersections of subbasic elements S, X, U, we get general basic element of this topology. One can observe that the topology of pointwise convergency on y to the power x is nothing new. As I have said already, it is just the product topology we have previously studied. Also, one can note that topology of capital X has not been used to define subbasic elements, hence it has not been used to define basic elements. The following theorem justifies the name of topology of pointwise convergency. A sequence fn of functions converges to the function f in the topology of pointwise convergency if and only if for each x in capital X the sequence fn x of points of y converges to the point fx in the topology of y. That means, if for each x the sequence fnx converges to the element fx and this convergency in y, that means this convergency is depend only the point on x. That is the reason this convergency is called pointwise convergency. Let us consider the following example. Let R be with usual topology and consider R to the power I, where I is the unit interval 0, 1. Now, let us consider a sequence of continuous functions defined by fnx is equal to x to the power n. Then Fnx converges in the topology of pointwise convergency to the function f defined by fx is equal to 0 for all x strictly less than 1 greater or equal to 0 and is equal to 1 for all x is equal to 1. In fact, when x is less than 1, then the sequence x to the power n converges to 0. So, fx is equal to 0 when x is strictly less than 1. Now, if x is equal to 1, then the sequence xn converges to 1. Hence, fx is equal to 1 for x is equal to 1. But the function fx, which is the limit of the sequence fn in the topology of pointwise convergency, is not continuous at the point 1. This example shows that the set CIR is not closed in R to the power I in the topology of pointwise convergency. We now like to investigate one topology which behaves somehow like uniform topology. That is, in the previous example, we have examined that in the topology of pointwise convergency, it is possible that a sequence of continuous functions converges to a function which is not continuous. But in case of topology of uniform convergency, we know that a sequence of continuous function converges to a continuous function. So, this is natural to ask whether there exists any other topology in which case a sequence of continuous function converges to a continuous function. Our answer is topology of compacta convergency. So, let us give the formal definition. Let capital X be a topological space and YD be a metric space. Given an element f of y to the power x, a compact subset C of capital X and a number epsilon greater than 0, we denote BCF epsilon is equal to all those functions from x to y such that supremum of the set dfx gx such that x belongs to C is less than epsilon. That is, maximum distance between f and g on C is less than epsilon. It can be easily proved that the sets B, C, F epsilon form a basis for some topology on y to the power x. To prove this, let epsilon greater than 0, it is sufficient to show that if G belongs to B, C, F epsilon, then B, C, G delta is contained in B, C, F epsilon for some positive number delta. Now, if we choose delta is equal to epsilon minus supremum of the set D of fx gx where x belongs to C, then we get this inequality. This proves that the collection of the sets B, C, F epsilon where C is a compact set and F is a functions from x to y is a basis for some topology on y to the power x. This topology is called compact convergency, or sometimes the topology of uniform convergency on compact sets. The topology of compact convergency differs from the topology of pointwise convergency, which will be clear from the following discussions. But the following theorem of course justify the nomenclature of this topology. Theorem: let X be a topological space and YD be a metric space. A sequence Fn from capital X to Y of functions converges to a function f in the topology of compact convergency if and only if for each compact subset C of capital X, the sequence Fn restricted on C converges uniformly to F restricted on C. The proof in fact follows from the definition. In the definition, we have seen that the open sets or basic open sets in the topology of compact convergency defined as B, C, F, epsilon, that means all functions from x to y which are less than epsilon distance from f on C. From this definition, this theorem follows easily. So far in this module, we have discussed topology of pointwise convergency and compact convergency topology. Both this topology are defined on the space y to the power x. We have observed that topology of pointwise convergency is nothing except our previously defined product topology. Also, we have observed that in the topology of pointwise convergency, a sequence of continuous functions may not converge to a continuous function, but in the topology of compact convergency, a sequence of continuous functions should converge to a continuous functions. Let us come to the next part of the slide. Next, we shall proceed to establish the inclusion relations between the three topologies: topology of pointwise convergency, topology of compact convergency, and compact open topology. Definition: a space X is said to be compactly generated if any set A is open in X, provided that A intersection C is open in C for each compact subspace C of X. That is, the space capital X is compactly generated if given any compact subspace C of X, a subset of capital X is open if A intersection C is open in the topology of C, where topology of C is induced as a subspace from the topology of X. This has the also closed set version. The closed set version says that a space X is compactly generated if any set B is closed in X, provided that B intersection C is closed in C for each compact set C. Many familiar spaces are compactly generated. For instance, locally compact Hausdorff spaces are compactly generated. We know that most of the topological space are locally compact Hausdorff space. So, if we can prove that locally compact Hausdorff spaces are compactly generated, then we can say most of the topological spaces are compactly generated. So, to prove that locally compact Hausdorff spaces are compactly generated, let X be a locally compact space and let A intersection C be open in C for any given compact subset C of X. Note that here A intersection C is open in C. Now, given X belongs to capital A, let us choose a neighborhood U of X that lies in the compact subspace C of X. We can do this because X is locally compact. Now, since A intersection C is open in C, by locally compact hypothesis, A intersection U is also open in U and hence open in C, and therefore it is open in capital X. Thus, A intersection U is a neighborhood of X contained in E, so that A is open in capital X. Thus, locally compact Hausdorff spaces are compactly generated. Next, we prove that every first countable space is compactly generated. That means every metric space will be compactly generated. To prove this, let capital X be a first countable space and let B intersection C is closed in C for each compact subspace C of X. Note that here we are using the closed set formulation of the compactly generated sets. Now, let X be a limit point of capital B. We have to prove that X is in B. Since X is first countable, we know that there exists a sequence xn of points of B which converges to X. Then we can consider the subspace C defined by singleton set X union the range set of the sequence, that is xn such that n belongs to n. Then C is a compact subset of the first countable space capital X. Now, since C is compact, B intersection C is by our assumption is closed in capital C. Since B intersection C contains whole xn for every n, it contains X as well. Because X is a limit point of the sequence xn, therefore X belongs to B. Hence, we have proved that every first countable space is compactly generated. Next, we shall establish some relation between continuity and compactly generated sets. If X is compactly generated set, then a function f from x to y is continuous if for each compact subspace C of capital X, the restricted function f on C is continuous. That means if each function restricted on a compact subset is continuous, then f is continuous. To prove this, let f from x to y be a function which is continuous when restricted on compact sets, and we wish to prove that the function f from x to y is continuous. For this, let us consider V an open set in Y. We have to show that f inverse V is open in X. Now, given any subspace C of X, the following equality holds: f inverse V intersection C is equal to f restricted on C inverse of V. Now, if capital C is compact, then by our given hypothesis, as f restricted on C is continuous, we have that f restricted on C inverse V is open in C. Since capital X is compactly generated, it follows that f inverse V is open. This proves that f from x to y is continuous. Now, we prove that closeness of Cxy in x to the power y. Let X be a compactly generated space and let Yd be a metric space. Then Cxy, that is the collection of all continuous functions from x to y, is closed in y to the power x in the topology of compact convergence. To prove this, we have to show that any limit point of Cxy is in Cxy. So, let f be a function from x to y which is a limit point of Cxy. We have to prove that f is also continuous. Since x is compactly generated, it is sufficient to show that f restricted on C is continuous on C for any compact subset C. This follows from the previous lemma. Now, for each n, consider the neighborhood BCF 1 by n of f. Recall that this type of sets are the basic open sets of topology of compact convergence. Now, BCF 1 by n intersects Cxy for each n. So, we can choose a function fn in Cxy lying in this neighborhood. For each n we can do this. Then the sequence fn restricted on C from C to y converges uniformly to the function f restricted on C. This follows from a previous theorem. So that by uniform limit theorem we have that f restricted on C is continuous. Hence, by the previous theorem we can say that f is continuous. This proves that f belongs to Cxy, that is Cxy is closed in y to the power x in the topology of compact convergency. So, as a corollary, we can say that if X is compactly generated space and YD a metric space, then if Fn is a sequence of continuous functions from x to y which converges to f in the topology of compact convergency, then f is continuous. So, this answers our investigation that in which topology except topology of uniform convergency a sequence of continuous function converges to a continuous function. Now, we have three topologies for the function space y to the power x when y is metric space. The relation between them is stated in the following theorem, whose proof now is straightforward. Let X be a space and YD be a metric space. For the function space, one has the following inclusion of topologies: uniform convergency is contained in compact convergency is contained in pointwise convergency. That is, pointwise convergency is the biggest topology or is the finest topology. Now, if capital X is compact, the first two coincides, and if capital X is discrete, then second two coincides. So far in this module, we have discussed topology of pointwise convergency, topology of compact convergency, and we have established that topology of compact convergency is finer than the topology of uniform convergency, and topology of pointwise convergency is finer than topology of compact convergency. With this, we end this module. Let us pass to the next module.